Righty. All right, you two ready? All right, I'm going to give you some notes just to get you guys started. And then you can kind of choose what you want to work on. Like I said, I don't need you guys to fill in all the worksheets and things like that. If you just read it and understand it, you're fine. If you find at the end of this notes that you're like, oh, actually, this is fine, I don't need to do these iPad pages, then that's also okay. So let's talk about thermal energy. I probably should have done some notes, a bit more notes before, because I'm backtracking and I'm realizing, actually, let me give you some more information first. So when we're talking about the thermal section of this exam, we need to think about what thermal heat energy is, and we also need to think about what temperature is measuring. So I'm going to first start with temperature and what we're doing when we have a thermometer. So when we have something like temperature, so I have it on the board there too if you want to see it not upside down, we are just measuring how hot or cold a substance is. Now, when we are thinking about that, the reason why something is, hot or cold has to do with the movement of the particles. Are we okay with that so far? All right. So if something is cold, our particles aren't moving as fast as if something is hot. If something's hot, our particles are moving very, very fast. Are we okay with that? All right. The movement of the particles then is going to be based off of the thermal energy that the substance has. Which is based off the movement of the particles and also how many particles you have. Because the more particles that I have moving, then I have more thermal energy quantity-wise. The way that I like to think about it is, say, for example, you're trying to heat up some water in a kettle. You notice that in the kettle, it's a lot faster to heat that water if it's a small amount of water versus you fill the kettle completely. So that's why the amount of particles is important. Also think about like the different temperatures that you're heating the water. It's easy to heat, say, to like not boiling point, and then it's more energy to get it to boiling point. So those are two things to kind of consider. Are we okay with that so far? All right, so I'm just trying to see what I have in my notes. Cool. The next thing I need to talk about then is a concept that we actually do in level 3 chemistry. So I am quite I am quite concerned that this exam is using actually quite a bit of level 3 chemistry stuff in it, and this is a level 1 exam. So I question the logic in what they're doing, but that's okay. I'm teaching level 3 chemistry, so I can still help you guys through this. Something to keep in mind when we're talking about heating substances is which half of the substance is releasing the heat energy and which half is absorbing it. So we use specific terminology to help us categorize which one's which. So, for example, let me give you the definitions first. So exothermic is referring to any reactions that are releasing heat energy. Endothermic is absorbing heat energy. The way I like to, when you are releasing heat energy, for you in a reference point, it'll feel hot because you touch something and it's like, oh, ouch, that's hot. And that's because it's releasing heat energy. I think about exothermic as being excited, releasing all that energy. Endothermic, I think about the end, death. When you touch dead body, it's cold. So it's absorbing heat energy. When you feel something is cold, it's not that cold is being transferred to your hand. It's the loss of heat from your hand that's making that sensation of cold. Does that Makes sense. It's a weird kind of thing to kind of think about. So let me give you some examples because it's going to then apply to our heating and cooling curves. So let's say I have a pot on the stove. That's my element. That's my pot. And I'm trying to heat up some water. This, because the water is absorbing the heat energy from the element, is an endothermic reaction. Even though the water is boiling, that is endothermic itself, the transition from a liquid to a gas. So don't just think, oh, hot water, it must be exothermic because it's hot. Actually think about the chemical process that's occurring, and that is the boiling water is absorbing heat energy to boil. So boiling of water, melting ice, these are all absorbing heat. So therefore, this is an endothermic reaction. It's kind of counterintuitive, but it's important because we're going to talk about heating and cooling curves. If, on the other hand, I'm trying to get a tray of ice and I'm freezing it, like that. So if I'm trying to condense gas, liquid, or if I'm trying to freeze something, again, you might think, oh, it feels cold, so that way it must be endothermic. Again, you have to think about what's happening to that reaction. So for ice to be able to form, it needs to release its heat energy to the environment. Say, for example, a cold freezer that can accept that heat, and thus it cools it down. And so this reaction itself is exothermic. So this is releasing heat. Yeah. Are we okay with those ideas? Yeah, so it's a little bit counterintuitive, but that's what we're actually looking at. So if I was holding the ice in my hand and the ice was melting, I feel cold because an endothermic reaction is now occurring because the ice is melting in my hand. It's taking that heat energy from my hand in order to break the bonds to then transition from a solid state to a liquid state. So you got to be kind of on top of that. So let me talk about some of those SciPad pages. So that way we understand what's going on here. And then you guys can have a little bit of break and try to do some reading. So like I said, if you find after these notes that you got this, don't stress about doing those SciPad pages then. All right, so this is what's called a heating curve. There's going to be both a heating and a cooling curve. So what we're looking at here is heat being added to, say, for example, some ice, and the temperature of that ice and how that is changing. So for example, if the ice is stored in the freezer is at negative 20 degrees, and so the ice itself is at 20 degrees Celsius. When I take it out of the freezer, then it's going to start increasing its temperature. We notice at this point there isn't a state change. It's still in the solid state. But we notice the temperature of that ice is increasing. So it is absorbing heat energy. And what's happening when it absorbs that heat energy is that my molecules, because we're talking about water, they're starting to vibrate a bit faster. They're still bonded together, but they're just vibrating a bit faster. So they're all linked together. They're still just moving, but they're moving faster and faster. And because they're moving faster and faster, they're now hitting a higher temperature. So in this phase here, we're just thinking about the molecules are moving faster. Okay? Now, what you'll notice here is that it levels off for a period during that heat being added, and it stays constant. So now the temperature is staying constant and it's not changing. This is known as our melting point, and what's happening here is that instead of the energy going into making the molecules move faster, the energy is going into breaking bonds. So that's why the temperature is staying at 0. Okay with that. So you see a leveling off section. Once we have completely melted our ice and now we're in the liquid form, now the temperature can start increasing again because now I don't need to put in energy to break bonds anymore. Instead, now it's going into the molecules moving faster again. So we're doing that again. And then up here, we get another leveling point for boiling because once again, instead of that being used to make the particles move faster, it's being used to break the bonds between the water molecules. So again, that applies up there so that it levels out again. And then once it gets to the gas phase, it keeps heating and heating and heating. All right, so that's what we're looking at for a heating curve. So I just want to basically explain why are there these leveling out points? Now, looking at the pilot exam from last year, that was not covered as one of their questions. So I would say odds are they probably will ask that question. That's what I want to point out. Are we okay with that? Okay. So the next thing that we need to look at is the cooling curve. So basically this happening in reverse. So it's this guy over here. Just check my notes. All right. So in our cooling curve, again, we're talking about water. So we have the opposite occurring. We have water in the gas state as a vapor, and it's cooling it down so that way it changes states. So as we're cooling it down, remember that, like I said, this is going to be an exothermic reaction. It is releasing the heat energy into the environment so that way the molecules then start slowing down. So what we see here at this point, we have our gas, they're moving fast, and here we're starting to see that it's releasing energy to slow down. Say molecules are slowing down. Something that, again, I want you to keep in mind when we're talking about this is thermal energy is related to the movement of particles. So that's why I see that temperature that I'm measuring is going down because my particles are not moving as fast anymore. Then I hit a point where, again, my temperature doesn't change. It stays constant. And this is where condensation is occurring. So once again, instead of us losing energy from the movement of the particles, instead we are losing energy, the energy is getting released into the environment because bonds are being made. So bond making releases energy. So the energy is still getting released, but it's getting released again to the environment. The energy being taken away from the particles moving, which would have lowered the temperature, it's being released from the bonds instead. So we're still releasing energy, it's just coming from a different state and it's not actually affecting temperature at that point. And then once we go into our liquid phase and everyone has been condensed down from a gas to a liquid, then once again, we are releasing energy because the particles are slowing down. So that's going to the environment. And then again, you have that freezing point. So our particles are moving slower and slower, and then as it's freezing, it's getting colder and colder. There is actually a point where the particles stop moving when it gets cold enough to do that, and that's called absolute zero. There's lots of different temperatures, scales. We use Celsius because the nice thing about Celsius is that 0 for us on our marking point is frozen for water, and 100 then is our marking point for boiling water. So that's why we set it there. Obviously, there's different scales like Fahrenheit, where the freezing point of water and the boiling point of water are going to be different temperatures. Kelvin is the one that is set so that way the 0 mark is absolute 0. So that's what you're looking at. So those are my kind of notes for the beginning. Are there any questions? Nope. All right, I'll leave you to it for a little while. I'll check in again to talk about the heat capacity stuff, and then I'll cover this lesson. All right, I know it's a lot, unfortunately, for one lesson, but I'm trying to get everything done. So don't stress. You have the school holidays to do your learning. All right, cool. That's us.